My name is Rebecca Ansar. I will take you through my case study in medical diagnostics, creating a fine-tuned CNN model for malaria detection. Malaria is a serious disease caused by parasites transmitted to humans through bites from infected mosquitoes. Automating the classification of a human cell as parasitized or uninfected can facilitate early and accurate detection. In order to produce a high-accuracy malaria detection method, this project utilizes fine-tuning of a CNN model called Inception ResNet v2. Fine-tuning is a model-building method that harnesses the power of a sophisticated model architecture that is pre-trained on a large dataset. The Inception ResNet v2 model will be used here, which is trained on about 1 million images from the ImageNet database. The model architecture is customized by 1. Retraining a subset of the final layers in the model and keeping all other layer weights intact, and 2. Adding a custom head to the model that performs the specified task. In this project, that custom head performs a binary image classification task. It would not be possible to truly ascertain the benefit of implementing a fine-tuned CNN model unless there was a standard for comparison. A baseline CNN model is constructed in order to compare its performance with the fine-tuned model, which is built next. This baseline CNN model has a relatively simple structure made up of 3 convolutional layers with increasing filter counts of 32, 64, and 128. The model was fit using the training data, of which 40% was used by the model for validation. The baseline CNN model's final validation and test accuracies are both 95%, and its final validation and test losses are both 0.3. Next, the fine-tuned Inception ResNet v2 CNN model was constructed. The first step was to specify the convolutional base by accessing the Inception ResNet v2 model. The convolutional base weights were taken from ImageNet. The Inception ResNet v2 convolutional base is quite long and sophisticated. The final decision was to unfreeze and set to trainable the last 28 convolutional base layers. The model has a custom dense classifier as its head, with a dense layer that has 256 filters and the same final output layer specifications as the baseline CNN model. The final validation accuracy was about 95%, while the final test accuracy was slightly lower at about 94%. The final validation and test losses were both about 0.3. The baseline CNN model's test accuracy is slightly higher than the fine-tuned CNN model's test accuracy. Considering that the test dataset has about 8,000 images, an accuracy of even 1% more means that about 80 more images get diagnosed correctly. So even a small increase in test performance is meaningful given the size of the test data and the project's goal. These are not the expected results, but they do showcase exactly why constructing a baseline model is important. The relatively simple baseline CNN model outperformed the far more sophisticated fine-tuned model. Thank you.